Hey everybody on the internets. One more video. Today we're going to go over topic 5.4, magnetic fields. Our first problem shows two wires carrying equal currents into the page, and we're asked to find the direction of the magnetic field at point P. So when we take a look here, we'll find that we have two wires, and we have to make one pretty big assumption, and that is that P, point P, is equidistant from both wires. Okay, that's not defined by the problem, so we have to kind of make that one assumption, but once we do that, that's the last piece that we need to solve this problem. Okay, so first step is to use a right-hand rule and find our field direction. Remember that each of these wires will have circular field lines around the wire, and we need to find the direction of that field. So we use right-hand rule. We point our thumb into the page, and we then find that our fingers are going to curl around the wire in the clockwise direction. And this says counterclockwise, which is not cool. There we go. Which makes perfect sense because it's that kind of day. Okay, so our field direction is clockwise. And another thing I want to point out here is that in both of these cases, our field line is perpendicular to this line from the point to the wire. Okay, and the reason that is the case is because if you look at the wire and you draw the circular field line around the wire, what you're going to notice is that the field lines are tangential to that circular, to that circle that you've drawn. And if they are tangential, then in each of these cases, we're going to have a perpendicular line from the center. Okay, so moving on. So we've drawn our arrows at P. So we've taken care of step number 2. We have our field line from, we have our field line for B sub 2 and B sub 1, which are just correlated to current 1 and current 2, as I've shown here. And if we look at the vertical components of our fields, what we're going to find is that these vertical components just cancel each other out. And all we're left with then is the horizontal component of both of our vectors. Okay, and that gives us then our direction. So if we only have a horizontal component left, then we really only have two choices for direction, either 0 degrees or 180 degrees, as measured off of the x-axis, and this one is obviously pointed at 180 degrees. Okay, note that if our currents were not equal, then these fields would not cancel out, and our resultant field line would be pointed in a slightly different direction. Okay. So for 5.22, we're asked to express the Tesla in terms of fundamental units. So I've suggested that you should look at the formulae in your data booklet, and there's only one that's relevant, and that is F is equal to Q times V times B. That is the charge of the particle times the velocity of the particle times magnetic field strength. So we then solve this equation for magnetic field strength, and a possible unit that we could go with is Newton per Coulomb meters per second, but this is not really the final form of this unit, right? There's other stuff going on here. We could call this a kilogram. We can convert newtons to kilogram meters per second squared, and we can convert coulombs to ampere seconds, and that gives us this value, which we can then simplify to the final form, kilograms per ampere second squared. Okay, and then there are all kinds of ways algebraically you could break this down, but this is the way I did it. You may have taken a different route, and that would be fine. Okay, 5.23, An electron approaches a bar magnet as shown in 5.59. What is the direction of force on the electron? The first thing we need to know is the direction of the magnetic field. So I've drawn here a magnetic field line going from north to south, as they do. And I've also shown here the velocity of my electron. Actually, that was given by the problem. We use the right-hand rule, but note that there's one tricky thing here. When we use our right-hand rule as given by the book, we map force and velocity and electric field direction onto our fingers. However, the direction of the magnetic... Sorry, that was distracting. I'm going to turn off notifications. So the right-hand rule, though, only tells us the direction for a positive particle. So when we apply our right-hand rule in this case, because we have a negative particle, we have to flip the direction of force. Okay. Note that because we can see both the direction of velocity and the direction of the magnetic field here on the page and in the Cartesian coordinate plane, we know right away that our direction of force is either going to be into the page or out of the page. So all we have to decide with the right-hand rule is which of those it must be. Okay, so 5.24, we have 3 wires carrying currents of equal magnitude, and the directions of the currents are shown. So we're asked to state the direction of the force on wire Z. So first thing we need to recognize is that at Z, the force from wire Y is going to be greater than the force from wire X. Why do we know that? We know that because the currents are of equal magnitude, but wire X is further away than wire Y. So what that means is the field from wire Y is going to be greater than the field from wire X. Okay, and here I show the net magnetic field. If we knew the values, we could calculate our net magnetic field at this point, but we do not. Once we know the direction of our net magnetic field, which is upward, then we can use the right-hand rule again and find our direction of force, and that will be 0 degrees. And if you need to review the right-hand rule, then make sure you do that as needed. Make a note. Okay, so 5.25. Figures 5.62564 shows a part... It's been a great day. A charged particle entering a region of a magnetic field that is directed into the plane of a page, as you can see here. And what we can also see is that this particle is curving. Okay, so justify why the charge is positive. So for part A, we just recognize here that if we apply the right-hand rule to this situation, it tells us that a charged particle would curve in this direction. If it were an electron, it would have force in the opposite direction, and the curve would be in the opposite direction. Okay, so then the particle is a proton, and they give us its mass and its charge, and they give us the magnetic flux density. Note that the charge is just the fundamental charge, so very straightforward. Calculate the radius of the proton's circular path. Okay, well, here's where things get a little bit tricky because we have not covered topic 6 yet, and you then would not know this equation, okay? So the derivation, just super quickly, is force is equal to QVB sine theta. And the formula given for centripetal force in your book is mv squared divided by radius, okay? So what happens is one of our velocities on each side cancels out. And in this case, we have a perpendicular our motion is perpendicular to the field, so that cancels out sine of theta, leaving the charge times magnetic field strength times mass times velocity divided by radius. Okay, once you know that, then it's a very simple matter to rearrange the equation and solve for radius and plug in your values, and you will find that your radius is 0.22 meters after you have done that. Okay, the proton enters the region of the field with a speed of 5.2 times 10 to the 6 meters per second. Calculate the time the proton spends in the region of the magnetic field. Okay, so first thing we need to do is find the distance. Okay, and what we have here is a quarter circle. So what that means is we need to find the circumference and divide that circumference by 4. So I've done that here. And again, we know the radius. I've left it in terms of pi because I was in a hurry and didn't want to use a calculator. And you can do that. It's easy. Okay, then it's just a very simple matter of using our distance velocity formula and velocity distance time formula and rearranging it for time. So I've done that here, and I take my distance, and at this point I do whip out my calculator, and I will get 6.6 times 10 to the negative 8 seconds. Okay, this value in the denominator, you will recall, is given to us in the problem above. Okay, next, 5.26 shows the path of a charged particle, and the particle goes through a thin metallic foil. So state and explain the direction of motion of the particle and the sign of its charge. So first thing we need to do is define the initial and final radius. So we find the direction by, again, using a right-hand rule, and our right-hand rule will give a positive charge. Okay, so here is a diagram of the right-hand rule. I probably should have included that earlier, but anyway, there it is. This is the right-hand rule for a positive charge. So what we have here is indeed a positive charge. So that tells us the direction, and now we just need to break it down by what's happening here. So our radius is decreasing, and we know from my previous derivation that force is inversely proportionate to radius. Okay, and we also know that radius is proportionate to velocity squared. So these are just a couple of things that we know if we break this problem down. It could also be proportionate to mass, but the thing about mass is unless you're going very, very, very fast, it's not going to change. And we have no indication that we're going at relativistic speeds. Okay, so we also know that kinetic energy is equal to 1/2 mass times velocity squared, which means that kinetic energy is proportionate to velocity squared. Well, we have two conditions here that seem to be aligned. So what we know from these two conditions is that if both of these are true, then kinetic energy is going to be proportionate to radius. So if our radius decreases, then kinetic energy is being lost. Okay, so what this tells us is that as our particle passes through the metal foil, some of its kinetic energy is lost. And that's what's happening. Okay, I'm officially very annoyed by problem 5.27 because it has a mistake. Justify why the proton in worked example 5.26 exits the region of the magnetic field with the same speed as that as the entry point. Well, this doesn't make sense for a number of reasons. First, we're not actually shown either the entry or the exit point. And in this case, as we've demonstrated, both velocity and kinetic energy are going to decrease. Okay, as we've dumped off some kinetic energy into this magnetic foil. So clearly this is not meant to be 5.26, but instead 5.25. So apologies for that if it's confusing you. You were right to be confused. This problem does work a lot better for 5.25. Okay, so here we see the particle entering the magnetic field and we see the particle exiting the magnetic field. So it's going to work better. Plus, there is no loss of kinetic energy, which will mean that our particle exits at the same speed. Okay, so as we know, the work done on a particle in a magnetic field is 0 because it's taking a circular path. Okay, so this is just one of those weird things you kind of have to get used to. And we'll look at it more next. We will look at it more next semester when we come back for topic 6. So if our change in work is 0, then our change in kinetic energy is 0, and kinetic energy is constant. And if kinetic energy is constant, then our velocity must also be constant, because mass here is not going to change at non-relativistic speeds. Okay, so as usual, let me know if you have any questions, and have a great day, gentlemen. Or ladies, any ladies watching, you're welcome to the videos as well. Or, you know, gender non-binary folks, you're cool too. You're welcome to watch also. Anyway.